Good afternoon. Now, we are going to talk about different mitigation methods. In the last lecture, we kind of looked at different types of vulnerabilities in cryptographic libraries, and now we are going to look at how do we mitigate some of these vulnerabilities. And here is a laundry list. I will go slowly and zoom into one of them. So, I will zoom into this particular one of identifying vulnerable states and transition, but other one I will just quickly go through. So, when you talk about power level vulnerability, some form of masking is usual, and any time in security domain you masking, and Niloth Pala is a leader on this area. So, anytime you talk about masking, then if you have a variable x, you want to mask it with something. Typically XOR is a very efficient area and performance efficient operation. If you mask with any key or any other variable, then whoever is looking at it does not get an idea about the variable x, and the recipient or when its absolute original value would be read, XOR has a duality property. You XOR it again with the same value, you get back the original value. Timing protection. Timing protection, if you kind of look at, let me illustrate that problem first for the timing protection. So, in elliptic curve cryptography, if you zoom in Montgomery and few other places, there are codes such as if key bit I equal to 1, then you do certain stuff, else you do certain stuff. Now, if you have a code like this, an attacker knows about it, then during the profiling of power, what is going to happen? You are going to see certain computation of certain type will be happening, and then little bit of time something else. You will be able to find a difference, and from that you will figure out where it is taking a long time. That is probably the if part, and where is a short time. So, this is the if part, this is the else part, the time, because here are the 4 instructions that will take longer to execute versus here are the 2 instructions. You still have to find the boundary where it starts, all that you have to do, but once you do that, this timing mismatch in the if and else, that is the vulnerability somebody will exploit to kind of figure out. Once you know this, you know more than something, then you know this bit is 1, this bit is 0 of the key bit, you already figured that out. Now, whether it is 1 1 or there are 2 1, that is kind of sometimes confusing, but whatever it is, because this computation is based on key value, that is a direct attack. Sometimes attack is not direct, timing imbalance, you figure out something, using that you figure out something, using that then you find the key bit, right, exactly the way Dr. Korfa talked about the AES attack, multi-layer one after another after another. Now, can anybody tell me what is the mitigation of such a vulnerability? If you have a code in your program of this nature, how do you mitigate it? Balancing, the balancing. So, basically if there were 4 instruction here and 2 instruction here, you add 2 more instruction here. So, balance it out, so that its kind of time is same. Same analogy happens even when any power side channel attack. This is the timing one. When power side channel attack, when people kind of look at something taking a long power, then less, then long, and then less, people can figure out, well, what operation is going on. How do we mitigate this story? Some operation is taking more, some operation is taking less. How do you mitigate? Of course, you would want the one which is taking less to compute such a way it takes less power, that would be ideal. Most of the time that is not possible. Whoever is taking less, you pull it up, you basically pull it up and make it take more. You pull it up and make it take more by adding lot of garbage instruction. It is not a good idea from power dissipation or area perspective, but that is basically the mitigation. So, that you kind of make a nice profile, but as you know, this simple power analysis attack will not work, but once you do correlation power attack or differential power analysis attack, then basically you might be able to still figure it out. So, that was the timing protection. Then fault injection by modular redundancy and multiplication. This one we already talked about, the rare nodes and branches. We talked about that can you reduce the rareness of the design and then kind of do the check. And leaky paths we talked about, if we can compute leaky paths and designer get to know about it, then designer will try to see how do I stop, pause or add some stuff to kind of make sure those leaky paths does not exist anymore, right. So, let me now zoom in and spend little time to kind of show the FSM state vulnerability elimination, that basically solution is kind of integrated in Synopsys tool. Before I go there, for software modules, so the previous ones are applicable for software as well as hardware. Many of the software modules, the kind of some of the techniques that either exist or we proposed or somebody proposed, as you can see there is not a laundry list of items, it is mostly blinding and kind of temporal duplication. And so, in this particular case blinding is something different, it is not kind of extra. If you recall, for RSA, the encryption, when we are trying to do encryption of a message, we are basically trying to do, we are taking the message, we are doing the public key of where we are trying to send modulo the n, that is what we are trying to do. All you have to do extra here, you add for blinding, you add a random variable. So, first of all it has to be a random number between 1 and n, and it has to be relatively prime to n, just to not violate any of the characteristics of RSA algorithm. Then, and if I implement that in software, this is exactly how it would look. You are just basically trying to do this R, you are basically going to introduce there, right. And by using their existing library and functions, it is actually simple 1 or 2 line of code addition, that would be your mitigation for the software. And remember, you have that Witchy proof test. So, once you do the mitigation, now you run the Witchy proof test to see if you still have the vulnerability or blinding actually took care of it. Any questions? So, let me now go back to the state machine and kind of zoom in how this vulnerability mitigation happen. I am taking an example of a doorknob, but basically most of the cryptographic libraries has the finite state machines, and those finite state machine has the encoding, either you explicitly stated the encoding or after synthesis encoding happened, and those encoding will have values, those states will have values. And then problem is when you have those values and if you kind of want to unlock the door. So, from the door locked state, all you have to do flip just this particular bit to 1 and that would let you get in. We talked about it, and the reason it works. So, the kind of analysis we want to do on any kind of security algorithm is that we want to divide the all possible states in different categories, and typically these are the kind of 3 categories we consider. The one in the green is kind of anybody, it is a non protected states, and then the ones that through password check or whatever can go to some of the protected states. So, this is basically unprotected, this is basically outsider, unprotected, non protected, whatever that is. These we do not care, they are outsider. This one kind of authorize some people who are allowed to access the, and of course, these are the protected states, all these are protected states where you are changing the state or doing something important. These are protected state, and this dashboard which is somewhere in the middle, that is kind of authorization or authorized state. So, typically when you have a set of states, you want to divide them in certain classes based on your design. And why we are making this distinction? Because these states under no circumstances should lead to those red states, that is basically the idea. They should always go through authorization states, password check or whatever it is. So, that is what you want to check. And we talked about this hardware implementation earlier, where you said that all these state machines are implemented using a register. In the previous example, If you can just flip the first bit to 1, then we actually got the access. So, question is how do we, so what is our objective then? Let me go back and see if my capability, let me even go back further, one more step further. If this is my design, by changing one bit I can go to the unlock state just by changing one bit. What is my solution then? My solution depends on what is my laser capability. If laser capability is 1 bit, I want to make sure there is no state here in the unprotected state that can go in the 1 bit change to any of these, ideally the unlock state, right, or write password or unlock state. How do I achieve this? Let us focus on this sleep one, let us ignore. How do I achieve this? Yes, please.
Increasing the Hamming distance.
Increasing the Hamming distance. Right now Hamming distance is 1. If the capability is 1, I want to increase the Hamming distance to at least 2. If these are the only 2 states, if I could have made it 101, then that would have worked. Even if it can flip any of the 1 bits, it will still not match with the encoding of the protected one. So, the question is how do we find, and remember that finite state machine will have lot of states, how do we encode, how many bits are needed, how do you compute? We looked at basically couple of solution. So, exhaustive is of course interesting, you try all possible combinations and try to choose the encoding which is cheapest, a small number of bits. There is a work on probabilistic encoding. So, there are also work on somebody figured out the codes and there is a table lookup database, you can look it up. Given the number of states, given the Hamming distance if you are looking for, if you give them number of states and the Hamming distance, if you provide these 2 pieces of information, then they will give you the code. So, it is a huge code base, it may not fit for you, but then there is another one that probabilistically tries to figure out, and very quickly you will see it actually mathematically it is supposed to work, but real life it does not work. It took us some time. First of all, the dissertation was written in German, it took us some time to understand it, and then we kind of figured out. I will share that with you. Now, going back to the same, so the algorithm for this one, if somebody told me that the attack capability is 1 bit flip which is Hamming distance of 2 and there are n equal to 5 state, right. So, then we basically start with 3, if n equal to 5 we have to start with 3, right, you cannot start with 2, and if we start with 3, if we start 0 0 0, that is the first one, no problem, you keep it, and then if it is 0 0 1, this is not going to work. So, then has to be dropped. If it is 0 1 0, distance of 1 is not going to work. So, we really want distance of true, so that we can put in. So, this story kind of continues, we keep or we let it go, and some point 1 1 will not work and we are out with all the 3 bit encoding, but I have to cover 5 states. So, now I have to go for the 3 is exhausted, I have to go for the 4, and again in the 4 we can start with certain number and either we keep or we drop, and this story continues. In this particular case, this might be the answer. So, this is basically the key idea what we are trying to do, very simple idea, simple heuristic, and so by going back to that example, we basically exactly what we said 1001. So, then none of these unprotected states by 1 bit flip you will not be able to go there. So, basically what is the efficient way to find that state encoding, and this problem could be complicated. We kind of looked at that there could be a finite state machine which has a child finite state machine which would be a different kind of register encoding. How do you solve those problem, dependent and independent and hierarchical and all that. Now, in terms of kind of the results, as I said, the probabilistic one was kind of very interesting work, and as you will see it does not do well, but later we realize this probabilistic one actually do better when Hamming distance is really large, it does amazingly well. But for the finite state machine encoding, the Hamming distance the Hamming distance or the laser fault capability is really small, 1 or 2, maybe in the future 3 or 4. So, probabilistic actually does not do well for that. When you have a Hamming distance of huge, you are doing lot of mathematical computation where you need a code word, probabilistic does amazingly well. So, this is basically the kind of result that if you do a probabilistic for a very small, so laser fault capability of 1 bit flip, then with increasing number of states the probabilistic one really go high, but for a small number exhaustive and our approach is kind of fine, but as the number of bit flip capability goes up, then exhaustive is, as expected, exhaustive is going to do worse, because you are trying all possible combination. Probabilistic still does not do well, and this simple heuristic will do well. It is not optimal. So, there is a lot of scope for improvement, and in terms of even number of kind of looking at the encoding length, how many bits we needed given different number of states with different amount of bit flipping capability or laser fault power. If you kind of look at it, the probabilistic one actually do pretty bad because it is a small number of capability, but our results kind of closely matches with what exhaustive will find in terms of number of bits. It is just that exhaustive takes a long time to find it. Now, in terms of area overhead, when we kind of look, all of these techniques were applied on it, they were developed for cryptographic algorithms only. Really we are kind of looking at for these examples, as you can see, the protected states and non protected states on different types of design is actually not that much. It all depends on the algorithm, and then so the grouping is a kind of a another layer of advantage, which basically the key idea of grouping that we looked at. Without grouping basically means every state we kind of think of independent, and they should not travel from one to another. That is a very stricter condition. Instead, the grouping method said if you have 3 types of group, which is basically just think about the protected state, let us say this is think about a non protected state or maybe the authorized state. What we are saying is we actually do not care if a state here is trying to make a transition here, who cares? They are nobody anyway to start with. So, if anybody tries a laser fault injection, tries to go between them, we do not care. What we really care, I mean most importantly is the following: nobody from here should come to here, that we definitely care. As long as Hamming distance from any of the code word here is more than the flipping capability plus 1 distance away from here. Oh no, other way around, non protected state to protected states. As long as that distance is, that Hamming distance is more than bit flipping capability plus 1, then we are kind of do. That is the grouping approach. So, as a result, the grouping approach sometimes will do little better, but many cases it really did not do much. But the thing is, area overhead is not that much, because in addition to state encoding or case the number, you have so much of code in there. I believe that is pretty much all I had, and thank you for today. See you tomorrow at 10 o'clock.